All right, so we're going to continue to work with margin of error here. And we're going to work with this one. This is what, by the way, is called the point estimate. This is your best guess of the percentage of Americans that like pizza. And the author ventures that it sounds kind of low. Yeah, I wouldn't be surprised that could be a little bit higher, but the margin of error with this poll is plus or minus 3%. What is that plus or minus 3% saying? Can anyone put that into words? What's that saying about this poll? Yeah, it's saying this is just a number based on a poll. We think it's probably close, but it might not be particularly accurate, Layla. So it could be as high as 87% or as low as 81%. It's our margin of error because we don't know what the true value is. To know that true value, you'd have to talk to every American. And we can't even do that correctly in the census. The census undercounts a lot of population subgroups. So we've known since the 1940s or 30s that the census is off. In any case, it gives you this confidence interval. But we're going to look at these intervals a little bit different and try and tweak our intervals. See if we can't make our intervals smaller. An Associated Press poll indicated that 63% of teachers below college level feel like the amount of homework students get is not excessive. Do you think if I asked the students that you get the same answer? No? Probably not. It'd probably be kind of the reverse of this. The poll had a margin of error rate of 33.5% with a 95% confidence level. Now, the 95% confidence level talks about something that I'm not going to get into too much with this course, but basically it's saying that when you follow the correct procedures, 95% of the time, your confidence interval will contain that true population number, whatever the proportion should be. So let's take a look at our confidence interval. We've got 63% plus or minus 3.5%. Now on the low end, that could be 59.5. What is it on the upper end? What could the top end be? 66.5. So what I would have my stats students say about this is we can be 95% confident that the true proportion of teachers, and I'm not going to put in below college level because I don't want to make this too long, of teachers who think the amount of homework students get is not excessive is between these two numbers. True proportion of teachers who feel homework is not excessive is between, and these numbers, 59.5% and 66.5%. So somewhere in there. Now we don't know exactly where because we didn't talk to all the teachers. We just took a little sample, and that's fine. Nothing wrong with just taking a little sample. It's impractical and sometimes impossible to talk to everybody. So you're going to have to deal with sample data. Hopefully that sample data is representative. You've got a good representative sample and you can get good numbers out of it. There we go. Now sometimes we want to control the size of this because that margin of error might be too big. You might say, well, I need to know a little bit more accurately what this window of opportunity is for the true percentage. So we can control that. And sorry, I'm getting a little mixed up with all these sheets here. Let's say we wanted to control that error, control the size of the margin of error. That's what we're going to work with next. So, Wall Street Journal poll asks 1,000 Americans if they or family members ever been notified by a credit card company of a possible data breach. 45% said they had been notified. We can calculate the margin of error for that sample, and then see if we can't kind of, tweak our sample size in an appropriate way. So as a reminder, the margin of error formula is going to be this: 2 times the square root of p hat times 1 minus p hat over n. What in this problem would represent our p hat? Say again? Yeah, the 45. So that number here, that's going to be our p hat. So it's going to be 2 times the square root of 0.45. And tell you what, instead of actually just making our calculator do it, can anyone do 1 minus 0.45 in their head? What would that be? 0.55. You don't have to do it that way. That's fine if you don't. And we had 1,000 people in our sample. So let's calculate the margin of error that they should be reporting for this poll. Let's clear out a few things here. I want 2 times the square root. And here's a little bonus for those of you who happen to be here now and happen to have one of my graphing calculators. If you do the alpha key and then the x key, that'll let you do a fraction the way we would write it. And what I want to put in the numerator is 0.45 times 0.55 divided by 1,000. Okay, so we get a margin of error of about 3.1%. Are you comfortable calculating that margin of error? I mean, that's something that certainly you should expect to be quizzed on at some point. Okay, so we get about 3.1%. But the book's going to ask you to look back at that. So look back at that margin of error formula. What should happen to the size of the margin of errors if the number of people surveyed gets larger? We kind of looked at this a little bit ago. If I had 2,000 people instead of, say, 1,000 people, what should happen to that margin of error? Should decrease, right? So let's just check that again. So let me go back here. I'm going to hit the second key and then the enter key to bring up my previous calculation. Second and then enter. And let's just go back and edit this, put in a 2,000 as opposed to 1,000. Now, did it decrease by half? No, but that's okay. It's certainly less. So you're at about a 2% error sometime here now. So yeah, it's going to go down. So if the margin of error gets larger, the margin of error gets smaller. What I liken it to is you're getting more information by surveying more, and so you've got less of an error. Yes?
So the error, if you put like now 3,000, can it be 1%?
I'm not sure at what point it's going to cross 1%, but you're actually leading me in the direction I want to go. What if I wanted to control how big this was? What if I said, you know what, I want this to be 1%, because the seal really needs to know where this is at. She's really curious and won't accept a margin of error that's 3%, which when you go the plus and minus, now you got 6.2%. That's a lot of room. So you might want to control that error. So this problem is just saying that if we repeated this with, say for instance, a smaller number, then the error should get bigger. You can double check that yourself. Let's see, I've got to find the next page here. Give me a second, please. Here we go. So if you put in smaller numbers, you're going to get a wider margin of error. Not a big surprise there. So we're going to start reverse engineering these things so that we can do what Seal was asking, and that is, let's put in a margin for error and then figure out a value of n that's going to get us there. How big we're going to have to do that, or have to make that n. So we'll go along with problem number 9 as they kind of work our way through this. If you decide that you're only going to consider a survey solved in example 1 a success if the margin of error is at most 4%, it'd be perfectly reasonable to know how many, to want to know how many people you'd have to have in the survey, assuming that the result of 32% holds up. Set up the margin of error formula with 4% margin of error and a 32% sample proportion, and n representing the number of people in your survey. So basically what they're telling you is that our proportion here is 32%. The margin of error is going to be 4%. So we're going to set this formula up with those two things. So it's going to be 0.04 equals 2 times the square root of 32%, 0.32. And you can either put 1 minus 32%, or you could just put in 68% there, divided by n. So that's what they're asking you to do. Now we're going to have to solve for n. We're going to try and get n by itself. So the first step then we could do is try and get rid of this 2 out in front of the radical. I could divide both sides by 2. So, okay, let's divide both sides by 2. You get 0.02, that is 0.04 divided by 2, equals the square root of 0.32 times 0.68 over n. Okay. Now I've got to play around a little bit more. I eventually want to get rid of that radical. How could I get rid of the radical? Any suggestions? What's the opposite of the square root? Square it. Yeah, you're going to square both sides. So let's square both sides and see what we get. I'm missing a page here. So I'm just going to square both sides. It's going to be 0.02 squared equals square root of this, 0.68 over n squared. On the left-hand side, I think I'm going to get 0.00. Is it going to be 0.004? It's definitely going to get smaller. Yeah, it's going to be 3 zeros. 0.0004 equals 0.32 times 0.68 over n. Okay. At least we got rid of the square root. We're getting a little closer. We got to keep going a little bit farther though. So One of the problems that we're facing is that we've got that n is part of a denominator. So let me continue over here. 0.0004 equals 0.32 times 0.68. I should probably just multiply those together. I don't feel like it. Now, what I always tell my students when they're doing algebra problems like this, if you don't like the n in the denominator or the fact that you've got a fraction, let's get rid of it. The opposite of dividing by n would be to multiply by n. So n times both sides. That's going to give me 0.0004n equals 0.32 times 0.68. I'm almost done. I'm almost there. Divided by, what's multiplying the n? The 0.0004 is multiplying the n. The opposite of multiplying by something is to divide. So we'll divide both sides by 0.004n, 0.004n, or no, 0.004, 0.0004, and I get my number for n, 0.32 times 0.68 divided by 0.0004. Yay. All right. Let's actually calculate that number, see what that turns out to be. So 0.32 times 0.68 divided by 0.0004. Yay. So we get 544. If you get a fraction as part of this, if you got like 544.1, then round up, no matter what. In this particular instance only. Now that was a fair amount of work to get that number, right? So as a reward, as a bonus for you guys, we're staying extra. Let me give you a formula in general. So for your sample size calculation, and I'm assuming that we're going to be working with a 95% confidence interval here. It's going to be let's see, it's going to be n equals p hat times 1 minus p hat over the margin of error squared, where e is the desired margin of error. You have to write e as a decimal. And p hat is the proportion of success. Let's bring it back to a seal, because she asked a really good question earlier. It's like, well, wait a minute. I want to know where this is down to the 1%. How many people do I need to have in my study? So let's do that. For example, if p hat is about 32%, what size sample to get the error E down to 1%? Okay. Let's figure that out. It's probably going to be a lot. So in our case, that's going to be n equals 0.32 times 1 minus 0.32. What am I going to put down in the denominator? We've got to be careful. Don't say 1, because that wouldn't be quite right. Say again? Yeah. So it's going to be 0.01. 0.01. That's your margin of error, and it's going to be squared. Remember, you've got to write this as a decimal. So that's going to be 0.01. And that decimal term gets squared in the denominator, which makes it really small, which is going to make that quotient really big. So let's find out how big that's going to be. So let's see, 0.32 times 0.68. Oops, how about a 68? Divided by 0.01, and then I'm just going to hit the square key rather than type in 0.0001. Wow, a lot more people. But, you know, better accuracy. So it's about 2,176 people in order to get your interval down to 1%. Now you kind of got lucky here with your p hat. If p hat changes, then the number of people you're going to have changes too. Let's think of a different percent. Suppose that the success rate was more like 47%. So let me redo this calculation. If we had slightly different numbers, so like 0.47, and if that's 0.47, what's 1 minus 0.47? Anyone know? Yeah, 0.53, thank you. And watch what happens to your number of samples required. It changed, didn't it? So, you know, the sample size you need is going to depend on a couple things, one of which is going to be your margin of error. This part right here, that you can control. This might be a little bit out of your control, all right? You know, what p hat is. And there's a little trick that you can use. If you don't have an estimate of p hat, just use 0.5. 0.5 gives you kind of like, okay, this will definitely be enough. So if you don't know what p hat is, use 0.5. So then this formula really becomes 0.25 divided by e squared. That's kind of like the you don't know anything case. I don't think that's covered here, so we're not going to worry about that. But that'll do it. Cool. Thanks for sticking it out.